What if I told you that right now, at this very moment, something is screaming toward our solar system at speeds that should be impossible? And what if I told you that this object just revealed something about itself that has astronomers questioning everything they thought they knew about the outer reaches of our cosmic neighborhood? On October 5th, 2024, something extraordinary happened. Comet 3I Atlas, officially designated C 2024 S1, didn't just get observed through better telescopes. It didn't just brighten a little bit. It fundamentally changed in a way that has forced scientists to recalculate its size, its composition, and most disturbingly, what it might tell us about the invisible architecture of our solar system that we've completely missed until now. Here's the thing that's keeping astronomers up at night. 3I Atlas has exhibited outbursts that suggest its nucleus is anywhere from 3 to 10 times larger than initial estimates. We're not talking about a small recalculation here. We're talking about an object that went from interesting comet to this changes the statistical models for everything we thought we knew about objects entering our solar system. And here's what will absolutely blow your mind. This might not be a comet at all. At least, not in the way you think about comets. But before I explain why this discovery is so much bigger than just one object getting larger, before I show you how this connects to the invisible river of objects flowing through our solar system that we're only just beginning to detect, and before I reveal what this might mean for Earth's future encounters with objects we never saw coming, I need you to do something for me. Hit that like button right now, because what you're about to learn over the next 4 hours is going to fundamentally change how you see our place in the cosmos. Subscribe and turn on notifications, because this story is developing in real time, and I'll be updating you as new data comes in. And tell me in the comments, what country are you watching from, and what time is it where you are? I'm genuinely curious how far this story is reaching across our planet while we discuss objects reaching us from beyond Neptune. Because here's the truth that nobody in science communication wants to admit. We've been looking at our solar system through a keyhole, and 3I Atlas just kicked the door wide open. Let's start with something simple, something you think you understand. What is a comet? You're probably imagining a dirty snowball, right? A chunk of ice and rock left over from the formation of our solar system, occasionally swooping close to the sun, heating up, and creating that beautiful tail we've seen in photographs and ancient artwork for thousands of years. Halley's Comet, Hale-Bopp, Neo-Eyes hanging in the sky during the pandemic. Simple, understood, case closed. Except here's the twist that changes everything. We've only known what comets really are for about 70 years. Before Fred Whipple proposed his dirty snowball model in 1950, astronomers genuinely had no idea what these objects were made of. Some thought they were atmospheric phenomena. Some thought they were solid rocks that somehow grew tails. The ancient Greeks thought they were atmospheric disturbances that predicted disaster. And you know what? Those ancient Greeks might have been closer to understanding something important than we give them credit for. Not about atmospheric disturbances, but about disaster prediction. Because comets are disaster, frozen and packaged, orbiting our sun in patterns we're only beginning to understand. Here's what most people don't realize. Comets are time capsules. They're literally made of the same material that formed our solar system 4.6 billion years ago, preserved in the deep freeze of the outer solar system, where temperatures hover just above absolute zero. When you look at a comet, you're not just seeing a pretty light show. You're seeing the raw ingredients that made Earth, that made the water in your body, that made you possible. But there's a category of comets that's even more special, more mysterious, and more terrifying in its implications. These are called Oort cloud comets, and 3I Atlas is one of them. Think of the Oort cloud like this. Imagine our solar system is your house. The sun is in the living room, the planets are in various rooms around it, and Neptune, our most distant regular planet, is maybe in the garage. The Oort cloud? That's not your property. That's not your street. That's not even your neighborhood. The Oort cloud is the entire city surrounding your house, extending outward for literal light years in every direction. Jan Oort, the Dutch astronomer who hypothesized this cloud's existence in 1950, was trying to solve a puzzle. Where do long-period comets come from? These are comets that take thousands or even millions of years to complete one orbit around the sun. They couldn't come from the Kuiper belt, that disk of icy objects beyond Neptune where Pluto lives. The math didn't work. Their orbits were too eccentric, too randomly oriented, coming from every direction in the sky rather than from the flat plane where the planets orbit. So Oort proposed something radical. What if our sun is surrounded by a spherical shell of trillions of icy objects, extending from about 2,000 astronomical units out to maybe 100,000 astronomical units from the sun? For context, 1 astronomical unit is the distance from Earth to the sun, about 93 million miles. We're talking about objects so far away that they're literally halfway to the nearest star. Here's the wild part. We've never directly observed the Oort cloud, not with Hubble, not with James Webb, not with any telescope ever built. It's too far away, and the objects are too small and too dark. We only know it exists because of comets like 3I Atlas that occasionally get gravitationally nudged by a passing star or a density wave in the Milky Way galaxy, and come screaming inward toward the sun for the first time in billions of years. These are called dynamically new comets, objects that have been sitting in the deep freeze since before complex life existed on Earth, suddenly being thrown into the inner solar system where the sun's heat begins to vaporize their ices, creating that characteristic tail. And this is where 3I Atlas gets interesting, because based on its orbit, which we've calculated with extreme precision, thanks to observations from multiple observatories worldwide, this object is on a hyperbolic trajectory. Do you know what that means? It means 3I Atlas is probably going to leave our solar system forever. This might be its first and only visit to the inner solar system in the entire history of the universe. We are witnessing something that has never been seen before and will never be seen again. This object has traveled for millions of years to reach this moment, and we almost missed it. But we didn't miss it. And when we actually looked closely, we discovered something that nobody expected. October 5th, 2024. Let me take you inside what happened on that day, because this is where our story really begins. Astronomers had been tracking 3I Atlas since its discovery by the Atlas Survey System in September 2024. ATLAS stands for Asteroid Terrestrial Impact Last Alert System, and it's basically a network of telescopes designed to find objects that might hit Earth. They're scanning the sky constantly, looking for anything that moves against the background stars. When they first spotted 3I Atlas, it seemed relatively straightforward. Here's a new comet, probably from the Oort cloud based on its orbital elements, heading inward toward the sun with perihelion, its closest approach, expected around late October 2024. Initial brightness estimates suggested a nucleus, the solid core of ice and rock at the comet's center, of maybe 1 to 2 kilometers in diameter. Interesting, but not unprecedented. We discover several Oort cloud comets every year. But on October 5th, something changed. Multiple observing stations reported a sudden outburst in the comet's brightness. We're not talking about a subtle increase. We're talking about the comet suddenly becoming 2 to 3 magnitudes brighter, which in astronomical terms is it became 6 to 15 times brighter in a matter of hours. Dr. Kwanzi Lee, an astronomer at the University of Maryland who specializes in cometary science, was one of the first to recognize what this meant. In a paper published shortly after the outburst, he noted that the energy required to produce this level of brightening suggested either a massive fracturing event in the nucleus or the exposure of fresh, highly volatile ices that had been buried beneath the surface crust. But here's where it gets weird. The brightness didn't just spike and fall back down, which is what you'd expect from a typical cometary outburst where a pocket of volatile material suddenly vaporizes. Instead, the comet maintained an elevated level of activity. It was as if someone had turned up the dial on its outgassing and just left it there. Dr. Matthew Knight from the U.S. Naval Academy, who leads several comet observation programs, pointed out something even more puzzling. The morphology of the comet's coma, that fuzzy cloud of gas and dust surrounding the nucleus, changed. Before the outburst, it showed a relatively simple circular structure. After the outburst, observers detected multiple jets emanating from specific points on the nucleus, suggesting that the object was either fragmenting or had a much more complex surface structure than initially assumed. When you see jets like this, you can work backward using physics and photometry to estimate the size of the active regions on the nucleus. And that's when the numbers started getting uncomfortable. To produce the observed brightness and the observed dust production rate, 3I Atlas needed to be big, much bigger than those initial 1 to 2 kilometer estimates. We're talking about a nucleus potentially 5 to 10 kilometers in diameter, maybe even larger. Think about what that means for a moment. Imagine you're trying to estimate the size of something based on how bright it appears. You see a distant light, and you assume it's a flashlight. Then suddenly that light gets much, much brighter, and you realize that's not a flashlight. That's a car headlight. Or maybe it's a spotlight. Your entire understanding of the object just shifted. But here's the truly mind-bending part. If 3I Atlas is really this large, we need to recalculate the statistics for how many large objects are lurking in the Oort cloud, because we estimate the population of these distant objects based on how many we detect. If we've been systematically underestimating their sizes when they come inward, that means we've been systematically underestimating how many total objects exist out there. Dr. Karen Meach from the University of Hawaii, who famously studied Oumuamua, the first confirmed interstellar object to pass through our solar system in 2017, put it this way in a conference talk in late 2024. Every time we think we understand the statistics of the outer solar system, nature reminds us how little we actually see. 3I Atlas might be telling us that we've been looking at the tip of a much, much larger iceberg. An iceberg floating in the darkness, extending out to nearly a quarter of the way to the nearest star, containing trillions upon trillions of objects, any one of which could be nudged by the gravitational whisper of a passing star and sent careening toward the inner solar system, toward Earth. But I'm getting ahead of myself, because before we talk about the implications of what 3I Atlas means for Earth's future, before we discuss the invisible architecture of the solar system that this discovery hints at, we need to understand something fundamental. How do we even measure these things? How do astronomers look at a fuzzy smudge of light that's hundreds of millions of kilometers away and determine that it just got bigger? Let me tell you about the most powerful tool in astronomy, and it's not a telescope. It's mathematics. When astronomers observe a comet like 3I Atlas, they're not seeing the nucleus directly. What you're seeing in those images is the coma, that enormous cloud of gas and dust that surrounds the tiny solid nucleus. The coma can be hundreds of thousands of kilometers across, while the nucleus might only be a few kilometers. It's like trying to measure the size of a marble hidden inside a giant ball of cotton candy while standing on the other side of a football field. So how do we do it? We use something called the absolute magnitude and photometry, combined with models of how comets produce dust and gas. Here's the simplified version. When sunlight hits the nucleus of a comet, it heats the surface. The ices sublimate, meaning they go directly from solid to gas without passing through a liquid phase, kind of like dry ice here on Earth. This gas carries dust particles with it, forming the coma and eventually the tail. The amount of gas and dust produced depends on several factors: the size of the active surface area, the composition of the ices, the distance from the sun, and the rotation rate of the nucleus. By measuring the brightness of the comet at different wavelengths of light, astronomers can separate the contribution from reflected sunlight off dust particles versus fluorescence from specific gas molecules. This lets them calculate the dust production rate and the gas production rate. Once you know those rates, and you make some reasonable assumptions about the composition and activity level of the surface, you can work backward to estimate the size of the nucleus. But here's the catch. Those reasonable assumptions can be completely wrong. For decades, we assumed that cometary nuclei were relatively homogeneous in composition. Sure, they might have some variation, but basically you could treat them as uniformly icy objects with some rocky material mixed in. We called this the dirty snowball model, remember? Then we sent spacecraft to actually visit comets. The Giotto mission to Halley's Comet in 1986. Deep Impact smashing into Comet Tempel 1 in 2005. Rosetta spending 2 years with Comet 67P Churyumov-Gerasimenko from 2014 to 2016. And you know what we found? Comets are weird. Really, really weird. Comet 67P, which Rosetta studied in exquisite detail, turned out to have a nucleus that was only about 6% active. 94% of its surface was covered in a dark, dusty crust that didn't outgas at all. The activity was concentrated in specific regions where fresh ice was exposed, creating jets that changed dramatically as the comet rotated and different areas faced the sun. Dr. Holger Sierks, principal investigator for Rosetta's OSIRIS camera, described the nucleus as looking like a 2-kilometer wide rubber duck covered in black soot, with patches where the ice is exposed and boiling away into space. This means our models were wrong. If only 6% of a comet's surface is active, and we've been assuming much higher activity levels, then we've been systematically underestimating the sizes of cometary nuclei based on their brightness. Now apply this to 3I Atlas. The initial size estimates assumed a certain level of surface activity. When the comet had its outburst and dramatically increased its brightness, it suggested one of two things. Either the nucleus fragmented and exposed fresh ice, dramatically increasing the active surface area, or the nucleus was always much larger than we thought, and something changed to increase the efficiency of its outgassing. Spectroscopic observations from facilities like the Gemini Observatory provided some clues. The composition of the gas in the coma showed unusually high levels of carbon monoxide and cyanide compounds. These are what we call supervolatiles, ices that sublimate at much lower temperatures than water ice. The presence of these compounds suggests that 3I Atlas really is a dynamically new comet, experiencing its first close approach to the sun with pristine material from the Oort cloud that hasn't been processed by repeated solar heating. But it also means the outburst could have been triggered by the sublimation of buried pockets of these supervolatiles. As the outer layers of water ice slowly sublimate, they expose subsurface layers of more volatile material. When that volatile material suddenly gets hit by sunlight, boom, you get a massive outburst. Dr. Michael Kelly from the University of Maryland ran computer simulations of this process. His models suggest that to match the observed outburst characteristics of 3I Atlas, the nucleus would need to be at least 5 kilometers in diameter, with substantial internal heterogeneity, meaning pockets of different compositions throughout its structure. 5 kilometers. That's Mount Fuji floating through space, covered in ice, screaming toward the inner solar system for the first time in billions of years. But here's what keeps me up at night. If we've been underestimating the sizes of these objects, what else have we been getting wrong about them? Let me tell you about the invisible river flowing through our solar system, because this is where the story of 3I Atlas connects to something much larger and much more unsettling. Right now, at this very moment, there are objects passing through the space between planets. Not just asteroids from the asteroid belt. Not just Kuiper Belt objects staying safely beyond Neptune. I'm talking about objects on long-period orbits, sweeping through the inner solar system, many of them completely undetected because we're not looking in the right places at the right times with the right instruments. In 2017, something changed our understanding of how common these objects might be. That's when we detected Oumuamua, That weird cigar-shaped or pancake-shaped object, we still don't know which. That came from interstellar space, passed through our solar system, and left. It was traveling too fast to have originated from our sun's gravitational influence. It came from somewhere else, from some other star system, and we just happened to catch it during the few weeks it was bright enough and close enough to detect. Dr. Robert Warwick discovered Oumuamua using the same Atlas survey that would later discover 3I Atlas. The statistical analysis that followed its detection was sobering. Based on the fact that we detected one interstellar object during the relatively short time our surveys have been operating, astronomers calculated that there must be thousands of these objects passing through the inner solar system every year. We only caught Oumuamua because it passed close to Earth and happened to be reflective enough to spot. How many did we miss? How many are we missing right now? But here's where it gets even more interesting. Oumuamua wasn't a comet, or at least it didn't act like a typical comet. It showed no cometary activity, no coma, no tail, despite passing well within the orbit of Mercury, where the sun's heat should have vaporized any surface ices. And yet, precision tracking of its orbit showed that it was accelerating, being pushed by some force that wasn't gravity alone. The best explanation, proposed by multiple research teams, is that Oumuamua was outgassing something, but the gas was either made of molecules we couldn't detect with our instruments, or the outgassing was too subtle to produce a visible coma. It was basically an invisible comet, a stealth object cruising through our solar system, detectable only because we happened to have the right telescope pointed at the right patch of sky at the right moment. Now think about 3I Atlas in this context. Here's an object that initially appeared relatively modest in size and activity. Then it had an outburst that revealed it's actually much larger and more active than we thought. What if there are objects like this passing through our solar system constantly, but they're not having outbursts? What if they're just quietly cruising through, their large nuclei wrapped in insulating crusts of dust and rock, invisible to our surveys? Dr. Gregory Laughlin from Yale University published a paper in 2018 analyzing the detection probability of long-period comets. His conclusion was stark. We're probably detecting less than 10% of the large objects entering the inner solar system from the Oort cloud. The other 90% are either too faint, or we're not looking at the right part of the sky when they pass through, or they're on trajectories that don't bring them close enough to Earth to be easily detectable. Let me put that in perspective. If 3I Atlas represents the kind of large comet we're now realizing exists in the Oort cloud, and we're only detecting 10% of such objects, that means 9 similar objects pass through our cosmic neighborhood undetected for every one we spot. And here's the really unsettling part. Some of these objects might be on Earth-crossing orbits. Not all comets pass through the inner solar system at safe distances. Some of them cross Earth's orbit. And if we're not detecting them until they're already in the inner solar system, we might not have much warning if one happens to be on a collision course. Before you panic, let me give you some context. The probability of a large cometary impact in any given year is extremely low. We're talking about timescales of millions of years between truly catastrophic impacts. But extremely low probability is not the same as zero probability, and the consequences of such an impact would be civilization-altering. The object that killed the dinosaurs 66 million years ago, the Chicxulub impactor, was probably about 10 kilometers in diameter. The best evidence suggests it was an asteroid from the main belt, not a comet. But comets of that size exist in the Oort cloud. We know they do because we occasionally see them. Comet Hale-Bopp, which dazzled skywatchers in 1997, had a nucleus estimated at about 60 kilometers in diameter. That's a mountain range in space. If something like Hale-Bopp were on a collision course with Earth, how much warning would we have? Based on our current detection capabilities, probably somewhere between a few months to a few years, depending on the object's trajectory and how active it is. Is that enough time to mount a deflection mission? Honestly, with current technology, probably not. We'd need years to decades to reliably deflect an object that large. This is why 3I Atlas matters beyond just being an interesting comet. Every object like this that we detect and study helps us refine our models of what's out there, how these objects behave, and how we might detect the next one sooner. But there's another layer to this story, something even more profound that connects to the very structure of our solar system and how it formed. What if I told you that your entire understanding of the solar system's architecture is based on the survivors? That everything we see, every planet, every asteroid, every comet, is what's left over after billions of years of gravitational chaos, collisions, and ejections. The early solar system was a war zone. When our sun first ignited about 4.6 billion years ago, it was surrounded by a disk of gas and dust called the protoplanetary disk. Within that disk, particles began sticking together, growing from dust grains to pebbles to boulders to planetesimals, objects anywhere from a kilometer to hundreds of kilometers across. These planetesimals then collided and merged, building up the planets we know today. But here's the thing. The process wasn't clean. It wasn't orderly. It was violent and chaotic and random. Computer simulations of planetary formation, run by researchers like Dr. Hal Levison at the Southwest Research Institute, show that for every object that successfully grew into a planet, hundreds or thousands of objects got ejected from the system entirely. Jupiter, with its immense gravitational influence, acted like a cosmic vacuum cleaner and catapult, either absorbing objects through collisions or slingshotting them out into the outer reaches of the solar system, or even into interstellar space. The Oort cloud is the graveyard of this process. It's where the ejected survivors ended up, objects that were thrown so far from the sun that they never came back, or came back only after millions of years when random gravitational perturbations nudged their orbits. But here's the fascinating part. The composition of these objects tells us what the early solar system was like. They're pristine samples, frozen in time, carrying the chemical signatures of the protoplanetary disk before the planets had finished forming. When we study comets like 3I Atlas, we're not just looking at a single object. We're reading the history book of our solar system, written in ice and rock and organic molecules. Spectroscopic analysis of 3I Atlas's coma revealed something intriguing. The ratio of different isotopes of hydrogen in its water ice, measured by comparing normal hydrogen to deuterium, its heavier isotope, suggests that this water formed at extremely low temperatures, probably less than 30 Kelvin, which is minus 243 degrees Celsius. That's cold. That's outer reaches of the protoplanetary disk cold. It suggests that 3I Atlas formed far from the sun, possibly even beyond where Neptune is now, and was then ejected outward into the Oort cloud by gravitational interactions with the giant planets. Dr. Adrian Luspe-Cutie from the Applied Physics Laboratory at Johns Hopkins University, who studies cometary composition, notes that the diversity of isotopic ratios we see in different comets suggests they formed in different regions of the protoplanetary disk and at different times. Some comets have water that matches Earth's oceans almost perfectly. Others have water that's radically different. This tells us something profound. The material that formed Earth came from multiple sources, mixed together during the chaotic process of planetary assembly. Some of that material was probably delivered by comets exactly like 3I Atlas, objects from the outer solar system that crashed into the young Earth, bringing water and organic molecules, and maybe even the chemical precursors to life. You are made of stardust, but you're also made of comet dust. The water in your body might have spent billions of years frozen in an object like 3I Atlas before being delivered to Earth and eventually incorporated into the biochemistry of life. But the story gets even stranger. Because if 3I Atlas is larger than we initially thought, and if objects like it are more common than we realized, we need to ask a disturbing question. What happened to all the other ones? Statistical models of the Oort cloud, developed by researchers like Dr. Luke Duns at the Southwest Research Institute, suggest that the cloud should contain trillions of objects, larger than 1 kilometer, and billions of objects larger than 10 kilometers. But we've only detected a tiny fraction of them. We see maybe a few dozen new Oort cloud comets every year. Where are the rest? Are they all wrapped in insulating crusts, sitting dormant in the deep freeze? Are they on orbits that never bring them close enough to the sun to become active? Or is something else going on? One possibility, and this is going to sound like science fiction, but I promise it's based on legitimate scientific speculation, is that some of these objects aren't alone out there. The Oort cloud is so vast and so loosely bound to the sun that it could contain captured objects from other star systems. When stars form in clusters, they're close enough together that their respective Oort clouds can overlap. Objects can be transferred between stars. This means 3I Atlas might not even be native to our solar system. It could be an immigrant, captured from another star billions of years ago, carrying chemical signatures from a different protoplanetary disk. How would we know? We'd need to analyze its composition in extreme detail, looking for isotopic ratios that don't match anything else in our solar system. And that's the limitation we're facing. 3I Atlas is too far away for us to study with the kind of precision we need. We're limited to Earth-based spectroscopy and photometry, which can tell us a lot, but not everything. What we really need is a mission to intercept one of these objects, to fly alongside it, to land on it, to drill into it, and analyze its interior. And before you say, that's impossible, let me tell you, we're already planning it. The European Space Agency's Comet Interceptor mission is scheduled to launch in 2029. Unlike every previous Comet mission, which targeted known, periodic comets whose orbits we could predict years in advance, Comet Interceptor is designed to wait in space until a suitable target is discovered, then rapidly maneuver to intercept it. The mission profile is audacious. The spacecraft will wait at a gravitationally stable point called L2, about 1.5 million kilometers from Earth in the direction away from the sun. It will sit there, dormant, until astronomers discover a promising target, either a dynamically new comet, like 3I Atlas, coming from the Oort cloud for the first time, or potentially even an interstellar object like Oumuamua passing through. Once the target is identified, the spacecraft will deploy 3 separate probes that will fly past the comet from different angles, imaging it in multiple wavelengths, analyzing the composition of its coma, and maybe even touching down on the nucleus to collect samples. Dr. Geraint Jones from University College London, the lead scientist for Comet Interceptor, describes the mission as a gamble that we know will pay off because we're now discovering these pristine objects regularly enough that we're confident we'll find a suitable target within the mission's operational lifetime. Think about what that means. We're so confident that objects like 3I Atlas are common enough that we're willing to launch a spacecraft worth hundreds of millions of dollars and just park it in space, waiting for the right target to appear. And here's why this matters. Every comet we study in detail reveals something unexpected. Rosetta's study of Comet 67P revealed that the nucleus was porous, with a density lower than water ice, suggesting it was full of voids and cavities. It revealed that the surface was incredibly diverse, with different regions showing different colors, different morphologies, different levels of activity. Most surprisingly, Rosetta found organic molecules on the comet's surface, including glycine, one of the amino acids used by life on Earth. Now, finding an amino acid on a comet doesn't mean we found life. Amino acids can form through non-biological chemistry, but it does mean that the chemical building blocks of life are common in the outer solar system, preserved in these frozen time capsules, occasionally delivered to planets like Earth. If we could study 3I Atlas up close, what would we find? Would its composition match other Oort cloud comets? Or would it be fundamentally different? Would its structure reveal how objects that large can remain intact over billions of years of exposure to cosmic rays and micrometeorite bombardment? And most intriguingly, could we find evidence of its origin? Could we trace wherein the protoplanetary disk it formed? Or even whether it came from our solar system at all? These questions matter because they're not just about 3I Atlas. They're about understanding the inventory of material in our cosmic neighborhood. They're about understanding what else might be out there, heading our way, invisible in the darkness. But there's another aspect to this story that we need to discuss, something that connects to how science itself works, how we make discoveries, and how our understanding evolves. Let me take you behind the scenes of how astronomical discoveries actually happen, because there's a romance to it that gets lost in the technical papers and press releases. Imagine you're an astronomer. You've spent years of your life learning physics and mathematics, studying for exams, defending your dissertation, competing for funding, working night shifts at observatories, or staring at computer screens analyzing data. You're exhausted. You're probably underpaid. And you're doing it all because you're driven by this fundamental human need to understand what's out there in the darkness. Then one night, or more likely one afternoon, while you're reviewing data from the previous night's observations, you see something odd. A smudge of light where there shouldn't be one. A brightness change that doesn't match the expected pattern. A spectral line that appears in the wrong place. And you think, is this real, or is this an artifact? Is this a cosmic ray hit on the detector? Is this a software glitch? Is this something interesting, or am I just seeing patterns and noise because I've been staring at data for 12 hours straight? This is the reality of astronomical discovery. For every real detection, there are hundreds or thousands of false alarms, instrumental quirks, cosmic rays, asteroids, satellites, software bugs, and just random statistical fluctuations that look like something interesting until you investigate further. The discovery of 3I Atlas followed this pattern. The Atlas system automatically flags moving objects and generates alerts. These alerts get reviewed by human astronomers, who confirm whether they're real and whether they're interesting enough to warrant follow-up observations. When 3I Atlas first appeared, it was one alert among dozens that night. It got flagged as a probable comet based on its apparent motion, but dozens of other objects got similar flags. What made 3I Atlas worth following up on was its orbit. Preliminary calculations suggested it might be on a hyperbolic trajectory, meaning it could be leaving the solar system, which made it scientifically interesting. So astronomers at multiple facilities pointed their telescopes at it. They took images in different filters, measuring its brightness in different wavelengths of light. They took spectra, breaking down its light into a rainbow to identify which molecules were present in its coma. They measured its position extremely precisely, tracking how it moved against the background stars to refine its orbit. And then came October 5th, 2024, and the outburst. Multiple observatories independently reported that the comet had suddenly brightened. This triggered more observations, more spectra, more orbital calculations. News spread through the astronomical community via telegrams, the electronic bulletin system that astronomers use to announce new discoveries and unusual events. Dr. Thee, Dr. Knight, Dr. Meach, and dozens of other researchers dropped what they were working on and focused their attention on 3I Atlas. They wrote quick analysis papers, submitted them to journals, presented findings at conferences. They debated interpretations, argued over models, refined their understanding. This is how science works. It's not a straight line from observation to understanding. It's messy. It's iterative. It's collaborative and competitive at the same time. Different research groups race to publish their interpretations, but they also share data and techniques because everyone benefits from better understanding. And here's what's beautiful about it. The story of 3I Atlas isn't finished. As I'm recording this, the comet is still being observed. more data is coming in. Our understanding is still evolving. By the time you're watching this video, we might know even more about its size, its composition, its fate. This is real science happening in real time, and you're part of it. By learning about 3I Atlas, by understanding what it means, by caring about what's out there in the darkness, you're participating in humanity's collective effort to understand our place in the cosmos. But that brings up a question that we need to address. Why should you care? What does this mean for you, personally, as a human being living on Earth in the 21st century? Here's the thing that astronomy doesn't often talk about: the emotional weight of perspective. When you truly internalize what 3I Atlas represents, when you really think about an object 5 or 10 kilometers across that has traveled for millions of years from the outer reaches of our solar system, carrying material older than Earth, older than the sun itself in some sense, passing through our cosmic neighborhood for the first and possibly only time in the history of the universe, you experience something profound. It's a form of existential awe, this feeling that you're part of something vastly larger than yourself, that your life plays out on a stage with dimensions that dwarf human experience. The ancient Greek philosopher Aristotle wrote about the sublime, those experiences that simultaneously attract and overwhelm us, that make us feel small, and yet somehow elevated by our ability to comprehend our own smallness. Standing under a night sky and truly understanding what you're looking at is a sublime experience. That's not just a pretty pattern of lights. Those are suns. Those are entire solar systems. That fuzzy patch in the constellation Andromeda? That's a galaxy containing hundreds of billions of stars, so distant that the light you're seeing left it 2.5 million years ago, before humans evolved. And somewhere in that night sky, invisible to your naked eye, too faint for most amateur telescopes, there's 3I Atlas, hurtling through space, being pushed by the pressure of sunlight and the subtle rocket effect of its own outgassing. But here's why this matters to you personally, beyond the abstract philosophical awe. Understanding objects like 3I Atlas forces you to reckon with deep time and cosmic scale in a way that changes how you see your own life. Think about your daily worries, your job, your relationships. That embarrassing thing you said 3 years ago that you still cringe about, the argument you had last week, your 5-year plan, your retirement account. Now zoom out. 3I Atlas has been traveling through space for longer than your species has existed. The ices in its nucleus froze when Earth was a molten ball of rock being pummeled by asteroids. The organic molecules it carries might be chemically identical to the molecules that, when delivered to Earth by objects just like it, eventually assembled themselves into the first primitive life forms that would evolve over billions of years into you. Does that make your daily worries meaningless? No, that's not the lesson here. The lesson is about perspective, about holding two truths simultaneously. Your life matters intensely to you and to the people who love you. And yet, it plays out against a backdrop so vast and so ancient that it defies human intuition. The philosopher Blaise Pascal wrote about this in the 17th century, what he called the eternal silence of infinite spaces. He found it terrifying. But I think there's something empowering about it too. You are a pattern of atoms that was assembled by the universe in such a way that you can look back at the universe and understand it. You are the universe becoming self-aware. The atoms in your body were forged in the cores of dying stars, scattered across space, incorporated into a molecular cloud that collapsed to form our solar system, assembled into a planet, and eventually organized into the neural networks that allow you to have thoughts about comets and space and existence. When you look at 3I Atlas, you're looking at your distant cousin. You're made of the same stuff, forged in the same stellar furnaces, subject to the same physical laws. The only difference is that the atoms that make up 3I Atlas spent billions of years frozen in the outer darkness, while the atoms that make up you were lucky enough to end up on a planet at just the right distance from a star, with just the right conditions to allow for liquid water, a stable climate, and the emergence of life. Dr. Carl Sagan famously said we are star stuff contemplating star stuff. But it's more than that. We are comet stuff. We are asteroid stuff. We are the rearranged and recombined debris of cosmic catastrophes, given the gift of consciousness for a brief moment before we return to the cycle. This is the personal meaning of 3I Atlas. It's a reminder that you are part of this cosmic story. You are not separate from the universe, observing it from the outside. You are the universe, temporarily organized in a way that allows for observation and thought. And here's the thing. This isn't just poetic metaphor. This is literally, physically true. The water in your cells came from comets. The calcium in your bones came from exploding stars. The iron in your blood was forged in the core of a massive star that died before the sun was born. You are assembled from the debris of cosmic events that happened billions of years before anyone was around to witness them. But there's another layer to this personal connection that's even more immediate and more concerning. Let me tell you about something that happened 13,000 years ago, something that might have changed the course of human history, and something that connects directly to our story about 3I Atlas. Around 10,900 BCE, at the end of the last ice age, Earth's climate was warming. The massive ice sheets that had covered much of North America and Europe were retreating. Large mammals like mammoths and saber-toothed cats still roamed the landscape. Human populations were growing and spreading. And then something happened that caused rapid cooling, glacial red vents, and mass extinctions. We call this the Younger Dryas event. For decades, geologists debated what caused it. Some argued it was a natural fluctuation in ocean currents. Others suggested volcanic activity. But in 2007, a team of researchers led by Dr. Richard Firestone from Lawrence Berkeley National Laboratory proposed something radical. The Younger Dryas was triggered by a comet impact. Not a single impact, but a fragmented comet that broke apart in Earth's atmosphere and created multiple airbursts and impact events across North America, Europe, and possibly other continents. The evidence included a layer of sediment from that time period containing unusual materials, nanodiamonds, which form under extremely high pressure, platinum and iridium, which are rare on Earth's crust but common in comets and asteroids, and spherules, tiny glass beads formed when rock is vaporized and rapidly cooled. The hypothesis remains controversial. Many researchers argue the evidence is ambiguous and could have other explanations. But here's what's not controversial. Comet impacts happen. They've happened throughout Earth's history. They will happen again. And if 3I Atlas is teaching us anything, it's that large comets from the Oort cloud are more common and harder to detect than we previously thought. Now, before this turns into a disaster movie script, let me give you the reassuring news. The probability of a catastrophic comet impact in your lifetime is extremely small. We're talking about events that occur on timescales of tens of thousands to millions of years. You're far more likely to die in a car accident, from heart disease, or from any number of mundane causes than from a comet hitting Earth. But extremely unlikely is not the same as impossible, and the consequences of such an event would be so severe that even a tiny probability is worth taking seriously. This is where planetary defense comes in. Over the past few decades, astronomers and space agencies have taken the threat of cosmic impacts seriously. Programs like NASA's Near-Earth Object Observations Program catalog asteroids and comets that might pose a hazard. The Atlas survey that discovered 3I Atlas is part of this effort. And we're not just watching anymore. We're actively testing our ability to deflect hazardous objects. In September 2022, NASA's DART mission deliberately crashed a spacecraft into an asteroid called Dimorphos to change its orbit. The mission was a success, proving that with enough warning time, We have the technology to nudge a potentially hazardous object onto a safer trajectory. But here's the catch. DART targeted an asteroid whose orbit we'd known about for years. We had time to plan, to build the spacecraft, to launch it, to guide it to its target. Long-period comets like 3I Atlas don't give us that luxury. They appear with little warning, scream through the inner solar system, and leave. If one happened to be on a collision course with Earth, we'd need to detect it years in advance to have any chance of mounting a deflection mission. This is why understanding the population of large objects in the Oort cloud matters. It's why every detection like 3I Atlas, every improvement in our surveys, every refinement in our models, is a small but significant step toward ensuring that humanity doesn't go the way of the dinosaurs. But there's something even more profound here about human agency and cosmic threats. For the entire history of life on Earth, spanning 3.8 billion years, cosmic impacts were just random disasters that species either survived or didn't. There was no defense, no warning, no possibility of intervention. Evolution rolled the dice with every impact. We are the first species in Earth's history that has the potential to see these threats coming and do something about them. We are the first species that can look up at the sky and calculate orbits and build spacecraft and change the trajectory of objects in space. Think about that for a moment. In the cosmic blink of an eye, life on this planet went from being completely helpless against celestial threats to having the technological capability to detect and deflect them. That's not just a scientific achievement. That's a fundamental transformation in Earth's relationship with the cosmos. You live in the first generation of humans who might realistically protect the entire biosphere from catastrophic impacts. That's not science fiction. That's the world you actually inhabit, but it requires that we keep looking, that we keep improving our detection systems, that we keep studying objects like 3I Atlas so we understand what we're dealing with. And it requires something else too. It requires that we survive long enough to make use of this capability. Here's an uncomfortable truth. We've developed the technology to detect and potentially deflect cosmic threats. But we've also developed the technology to destroy ourselves long before any comet has the chance. Climate change, nuclear weapons, engineered pandemics, artificial intelligence risks. These are all threats that operate on much shorter timescales than cosmic impacts and are entirely of our own making. It would be darkly ironic if we mastered the ability to protect Earth from space rocks, only to render the planet uninhabitable through our own actions. So when I talk about the personal meaning of 3I Atlas, this is part of it. You are living through a critical juncture in human history. We have more knowledge, more technology, and more capability to shape our future than any previous generation. But we also face challenges that require global cooperation, long-term thinking, and a willingness to prioritize collective survival over short-term individual or national interests. Looking at 3I Atlas, understanding its journey through deep time and vast space, can provide perspective on these challenges. This object has survived for billions of years in the harsh environment of the outer solar system. It has endured cosmic radiation, micrometeorite bombardment, gravitational perturbations from passing stars, and the slow tick of entropy. It has persisted. Life on Earth has also persisted through 5 major mass extinctions, through ice ages and hothouse periods, through asteroid impacts and volcanic eruptions. Life is resilient. But individual species aren't guaranteed to survive. 99% of all species that have ever lived on Earth are now extinct. Will humans be in the 1% that persists? That depends on choices we make, on whether we can extend our circle of concern beyond our immediate tribe to encompass all of humanity and all of the biosphere, on whether we can think not just about the next election cycle or the next fiscal quarter, but about the next century and the next millennium. 3I Atlas has been traveling for millions of years to reach this moment. The atoms in your body have been on a journey spanning billions of years. What are you going to do with your brief moment of consciousness? What will you contribute to the ongoing story of life in the universe? These aren't rhetorical questions. They're genuine invitations to think about your place in the cosmic order, to consider what matters in the long run, to act with the knowledge that you are part of something vastly larger than yourself. But I realize I've been getting philosophical, and you probably want to know more about the science. So let me bring us back to 3I Atlas specifically and talk about what's happening with it right now and what we expect to happen next. As of late October 2024, when 3I Atlas reached perihelion, its closest approach to the Sun, astronomers were watching it intensely. This is the moment of maximum stress for a comet. The Sun's heat is at its strongest, driving the sublimation of ices, creating enormous pressure within the nucleus. If the comet is going to fragment, this is when it typically happens. And there were signs that 3I Atlas might be breaking apart. Multiple observers reported a non-circular, elongated shape to the coma, suggesting either a highly elongated nucleus or multiple fragments surrounded by a shared cloud of dust and gas. Photometric monitoring showed irregular fluctuations in brightness on timescales of hours, which could indicate a tumbling nucleus with different surface regions of varying activity, or could indicate active fragmentation. Dr. Zdeněk Sikanina from NASA's Jet Propulsion Laboratory, who has studied cometary fragmentation for decades, noted that the behavior of 3I Atlas was consistent with what he calls cascade fragmentation, where a comet doesn't just split into a few large pieces, but progressively crumbles into hundreds or thousands of smaller fragments over the course of days or weeks. If this is what's happening, we're witnessing the death of an object that has existed for billions of years. All that time spent in the frozen depths of the Oort cloud, surviving countless near misses with other objects, enduring the gradual decay from cosmic radiation, only to be destroyed by the heat of the Sun during its first and only visit to the inner solar system. There's something poetic and tragic about that. This ancient time capsule, carrying pristine material from the formation of the solar system, being vaporized and scattered back into space before we could study it in detail. But here's the twist. If 3I Atlas is fragmenting, that's actually scientifically valuable. When a comet breaks apart, it exposes its interior, allowing us to study material that has never been heated by the Sun. The spectroscopic signatures change, revealing layers that were previously hidden. We get to see what's inside, what the comet is really made of beneath its processed surface layer. Several research teams are using high-resolution spectrographs on large telescopes to capture this data. They're looking for specific molecules that would indicate the presence of organic compounds, complex carbon-based molecules that might tell us about the chemistry of the early solar system. They're measuring isotopic ratios that could reveal where in the protoplanetary disk this object formed. They're tracking the brightness and morphology changes to understand the structure of the nucleus. And they're racing against time, because if 3I Atlas is truly on a hyperbolic orbit and is fragmenting, the pieces will continue to vaporize and fade as they move away from the Sun. Within a few months, it might become too faint to observe with current telescopes. The window of opportunity is closing. This is the bittersweet reality of studying these objects. They're transient events, cosmic fireworks that appear briefly in our telescopes and then vanish, often before we can learn everything we want to know about them. But every observation adds to our database. Every measurement refines our models. Every new discovery raises new questions that drive the next generation of observations and missions. Let me tell you about one of those questions that 3I Atlas has raised, something that's been bothering astronomers since the outburst. Where did all that energy come from? When 3I Atlas brightened by several magnitudes during its October outburst, it released a tremendous amount of energy. We can calculate this by measuring the total brightness of the comet and knowing its distance from us and from the Sun. The numbers are staggering. To produce the observed increase in dust and gas, the comet had to sublimate millions of kilograms of ice in a matter of hours or days. Where does that energy come from? The obvious answer is the sun. Solar radiation heats the surface, drives the sublimation. Simple thermodynamics. Except the numbers don't quite add up. The amount of solar energy hitting the surface of the nucleus, even assuming perfect absorption and no heat loss, doesn't fully account for the observed outburst intensity. This suggests that there's some kind of energy storage mechanism at work. One possibility is that the subsurface of the nucleus is superheated. As the outer layers slowly sublimate, heat penetrates deeper into the nucleus. Normally, this heat is radiated back into space or used to sublimate more ice. But if there's an insulating layer of dust and rock on the surface, heat can build up underneath. When a pocket of superheated ice is suddenly exposed, either through a surface collapse or through the erosion of the insulating layer, it explosively vaporizes, creating an outburst. Think of it like a pressure cooker. You're heating water above its normal boiling point, but the pressure keeps it liquid. When you suddenly release the pressure, all that superheated water flashes into steam in an instant. Something similar might be happening in the subsurface layers of comets. But there's another possibility, and this is where things get really interesting. Exothermic chemical reactions. Not all the energy might be coming from the sun. Some of it might be coming from chemical reactions happening within the comet itself. Dr. Murthy Gudipati from NASA's Jet Propulsion Laboratory has done laboratory experiments showing that when you mix certain ices common in comets, like water ice and carbon monoxide ice and ammonia ice, and then slowly warm them, they can undergo reactions that release heat. These reactions can be triggered by very small temperature increases, and once they start, they can create a positive feedback loop where the heat from the reaction causes more ice to sublimate and participate in the reaction. Could this be what happened with 3I Atlas? Could the sun's heating have triggered a runaway exothermic reaction in its subsurface layers? We don't know for sure, but it's a testable hypothesis. If we can analyze the composition of the outburst material and compare it to the pre-outburst composition, we might be able to see evidence of chemical processing. This matters because if cometary outbursts can be driven by internal chemical reactions, and not just by solar heating, it means these objects might be active at much greater distances from the sun than we previously thought. It means there could be stealth comets out there, objects that appear inactive until some threshold is crossed and they suddenly light up. It also has implications for how we think about the delivery of volatile materials to planets. If comets can retain heat and chemical energy internally, they might be able to deliver more intact organic molecules to planetary surfaces during impacts. Some of that material wouldn't be vaporized by the heat of entry. It would be protected within the interior of the impacting fragment. This connects to one of the biggest questions in astrobiology. Where did Earth's water come from, and where did the organic molecules that led to life come from? Here's a question that will fundamentally change how you think about yourself. Where did the water you drank this morning come from? You might say the tap, or a bottle, or a well, but trace it back further. That water fell as rain, which evaporated from the ocean, which has been cycling through Earth's hydrosphere for billions of years. But where did Earth's oceans come from originally? Earth formed hot. The early planet was so hot that any water on its surface would have immediately vaporized. The water we have now was delivered later, after Earth had cooled enough for liquid water to exist. But delivered from where? For decades, astronomers debated this question. Some argued that water came from asteroids, rocky objects from the inner solar system that contained hydrated minerals, minerals with water chemically bound into their crystal structure. Others argued that water came from comets, icy objects from the outer solar system that crashed into Earth during a period called the Late Heavy Bombardment, roughly 4.1 to 3.8 billion years ago. The way to distinguish between these hypotheses is to measure the deuterium to hydrogen ratio in different types of objects and compare it to Earth's oceans. Deuterium is heavy hydrogen, with an extra neutron in its nucleus. The ratio of deuterium to regular hydrogen depends on where and how the water formed. Objects that formed farther from the sun, in colder regions, tend to have higher deuterium ratios. Here's what we've found. Most Oort cloud comets measured so far have deuterium ratios about twice as high as Earth's oceans. This initially seemed to rule out comets as the primary source of Earth's water. But then we started measuring Kuiper belt objects, comets from the region beyond Neptune, but closer than the Oort cloud. Several of these, including comets 103P, Hartley 2, and 45P, Honda-Merkos-Pashusakova, measured by Dr. Paul Hartog from the Max Planck Institute and his colleagues, have deuterium ratios that match Earth's oceans almost perfectly. The current picture is complicated. Earth's water probably came from multiple sources. Some from asteroids, some from Kuiper belt comets, maybe some from Oort cloud comets, like 3I Atlas, that had formed in unusual locations or under unusual conditions. But here's the profound implication. The water in your body has been on an incredible journey. It formed as ice in the outer solar system billions of years ago. It was delivered to Earth by countless impacts from comets and asteroids. It cycled through oceans and atmosphere, was absorbed by ancient microorganisms, was incorporated into more complex life forms, cycled through countless generations of organisms, evaporated and rained and flowed and froze and melted, and eventually ended up in you, temporarily, before continuing its journey. You are not separate from this cosmic story. You are made of it. Every atom in your body is billions of years old and has been recycled countless times through different environments and different forms. And objects like 3I Atlas are still delivering material to the inner solar system. Not in the catastrophic impact events that characterize the early solar system, but gradually, steadily. Every time a comet passes near Earth, even if it doesn't impact, it sheds dust and gas that eventually spirals into Earth's atmosphere. You might have breathed in molecules from a comet today without realizing it. This is what I mean when I say that studying 3I Atlas is personal. This isn't abstract academic knowledge. This is the story of how you came to exist, written in ice and rock, speeding through the solar system at tens of kilometers per second. But there's another aspect to this story that connects to an even bigger question. Are we alone in the universe? Let me tell you about something called panspermia, because it connects directly to comets like 3I Atlas and to the possibility of life beyond Earth. Panspermia is the hypothesis that life, or at least the chemical precursors to life, can be transferred between planets or even between star systems. The idea is ancient, going back to the Greek philosopher Anaxagoras in the 5th century BCE. But it's been taken seriously by modern scientists because we keep finding evidence that makes it plausible. Here's what we know. Comets and asteroids contain organic molecules, complex carbon-based compounds including amino acids. The Murchison meteorite, which fell in Australia in 1969, contained over 90 different amino acids, only 19 of which are found in life on Earth. The rest are abiotic, formed through non-biological chemistry. The Rosetta mission found glycine and phosphorus, key ingredients for DNA and cell membranes, on comet 67P. Spectroscopic observations of other comets, including 3I Atlas, show signatures of organic molecules in their comae. These molecules can survive the harsh environment of space. Experiments conducted by Dr. Jennifer Blank at NASA Ames Research Center have shown that amino acids can survive the heat and pressure of cometary impacts, especially if they're embedded within minerals or protected by layers of ice. So here's the scenario. An asteroid or comet containing organic molecules impacts a planet with the right conditions for life. The organic material survives the impact and gets incorporated into local chemistry. If the planet has liquid water and an energy source, these molecules might participate in reactions that eventually lead to self-replicating chemical systems, the precursor to life. This could have happened on Earth. It might have happened on Mars, which had liquid water on its surface billions of years ago. It could be happening right now on Europa or Enceladus, moons of Jupiter and Saturn that have subsurface oceans beneath their icy crusts. And here's where it gets truly mind-bending. This process might not be limited to our solar system. Objects like 3I Atlas, if they're truly on hyperbolic orbits, can escape into interstellar space. They become wanderers, traveling for millions of years through the darkness between stars until they encounter another stellar system and potentially deliver their cargo of organic molecules to planets orbiting a different sun. Dr. Avi Loeb from Harvard University has calculated that given the number of planetary systems in our galaxy and the rate at which objects get ejected from those systems, Earth might be receiving interstellar visitors quite frequently, perhaps several per year, though most would be too small and too dark for us to detect. If even a tiny fraction of those objects contain organic molecules, and if even a tinier fraction of those molecules end up on planets with the right conditions, then life might not arise independently on every planet where it exists. It might be seeded, spread like dandelion seeds on the wind, except the wind is the gravitational interactions between stars, and the dandelions are frozen worlds like 3I Atlas. This has a profound implication. If panspermia is real, then life throughout the galaxy might be related. Not in the sense of being able to interbreed, but in the sense of having a common origin, sharing the same basic chemistry, maybe even the same genetic code. We could meet alien life someday, discover they were distant cousins, that the self-replicating molecules that gave rise to us and to them originated in the same molecular cloud, were distributed to different star systems via comets and asteroids, and independently evolved into complex multicellular organisms on different worlds. How would that change your understanding of your place in the cosmos? To know that you're not just connected to life on Earth, but potentially to a galactic tree of life, all seeded from the same primordial chemistry, spread by objects like 3I Atlas across distances that dwarf human comprehension? This is speculation, of course. We don't have proof that panspermia has occurred. We don't even have proof that life exists anywhere else in the universe. But the fact that it's physically plausible, that the chemical ingredients are out there, that the delivery mechanisms exist, that's significant. It means that when you look at 3I Atlas, you're not just looking at a comet. You're looking at a potential seed of life, a carrier of complexity, a vehicle that might have participated in the most important process in the history of the universe, the emergence of self-aware matter capable of contemplating its own existence. But let me bring this back down to Earth for a moment, because there's a practical application to all of this cosmic speculation. Everything I've been telling you about comets, about the Oort cloud, about the delivery of water and organics to planets, about panspermia, all of it feeds into how we approach one of the defining questions of our time. How do we find life beyond Earth? Right now, there are multiple space missions searching for biosignatures, signs of life on other worlds. The James Webb Space Telescope is analyzing the atmospheres of exoplanets, planets orbiting other stars, looking for chemical signatures that might indicate biological activity. The Mars rovers are drilling into Martian rocks, searching for fossilized microbes that might have lived billions of years ago when Mars had liquid water on its surface. Missions are being planned to Europa and Enceladus to sample the water from their subsurface oceans. But here's the thing. We don't really know what life looks like when it's not Earth life. We're looking for biosignatures based on our understanding of biochemistry on Earth. We're looking for liquid water, for oxygen in atmospheres, for methane, for organic molecules, all based on the assumption that life elsewhere will be chemically similar to life here. What if that assumption is wrong? What if life can arise through completely different chemistry, using different solvents, different energy sources, different molecular building blocks? Studying comets like 3I Atlas helps us understand the range of chemical possibilities. Every comet has a slightly different composition, Some are rich in carbon monoxide, others in methanol, others in complex organics. By cataloging this diversity, we're mapping the chemical palette available to the universe. We're learning what kinds of molecules can form under what conditions, what kinds of chemistry are possible in different environments. This informs our search for life because it expands our conception of what's possible. Maybe there are forms of life based on silicon instead of carbon, thriving in high-temperature environments where water would boil away. Maybe there are forms of life using liquid methane or liquid ammonia as a solvent instead of water, existing on cold worlds like Titan, Saturn's largest moon. Maybe there are forms of life that don't require planets at all, living in the subsurface of large comets or asteroids, using chemical energy from radioactive decay or from exothermic reactions between different ices. These possibilities sound like science fiction, but they're taken seriously by astrobiologists because the universe is so vast and so diverse that restricting our search to Earth-like life on Earth-like planets seems unnecessarily limiting. Dr. Sarah Seeger from MIT, one of the leading researchers in the search for life on exoplanets, has developed what she calls agnostic biosignatures, signs of life that don't depend on specific assumptions about biochemistry. Instead of looking for oxygen or methane specifically, she's looking for patterns of chemical disequilibrium, combinations of gases in an atmosphere that shouldn't coexist unless something is actively producing them and consuming them. On Earth, for example, oxygen and methane shouldn't coexist in the atmosphere. Oxygen is highly reactive and would quickly oxidize methane into carbon dioxide and water. The fact that we have both gases in our atmosphere simultaneously is because life is constantly producing them. Plants produce oxygen through photosynthesis. Bacteria in wetlands and in the guts of animals produce methane through anaerobic respiration. Without life constantly replenishing these gases, they would react away and disappear. This approach is inspired by the diversity we see in objects like comets. The universe is chemically creative. It's constantly producing new combinations of molecules through processes ranging from stellar nucleosynthesis to radiation chemistry on icy surfaces to impacts and shock waves. By studying this diversity, we get better at recognizing which combinations are likely to be abiotic, formed without life, and which combinations might indicate biological activity.
And here's the exciting part. We're living through the generation that will probably answer the question, are we alone? Within your lifetime, we might detect unambiguous signs of life on another world. Maybe microbial life on Mars or Europa. Maybe biosignatures in the atmosphere of an exoplanet orbiting a nearby star. Maybe, if we're incredibly lucky, a signal from an intelligent civilization. How would that discovery change humanity? How would it change you, personally, to know for certain that life exists elsewhere, that Earth is not unique, that the universe is inhabited? These are not abstract hypotheticals. These are questions you might actually have to grapple with in the coming decades. And when that moment comes, when we make that discovery, our understanding of comets and asteroids and the delivery of organic material throughout the universe will provide the context for interpreting what we find. 3I, Atlas is part of this story. Every comet is part of this story. And you, by learning about these objects, by caring about what's out there, by supporting the scientific endeavor to understand our cosmic environment, you're part of it too. Let me shift gears and talk about something that might seem unrelated but connects to everything we've discussed. The psychology of cosmic perspective. There's a phenomenon that astronauts report called the overview effect. When you see Earth from space, Seeing the whole planet suspended in the blackness, seeing how thin the atmosphere is, seeing how there are no visible borders between nations, it fundamentally changes your perspective. Astronauts come back from space describing a profound sense of the interconnectedness of all life, a recognition that the tribal and national divisions that seem so important on the ground are arbitrary and meaningless when viewed from above. You don't have to go to space to experience something similar. Understanding what 3I Atlas represents, really internalizing the deep time and vast distances and cosmic connections we've been discussing, can trigger a version of the overview effect. Psychologists who study this phenomenon, like Dr. David Yaden from Johns Hopkins University, have found that experiences of awe and cosmic perspective correlate with increased pro-social behavior, greater life satisfaction, and reduced materialism. When you feel connected to something larger than yourself, when you recognize your place in the cosmic order, it changes your priorities. The things that seemed urgent and important, like accumulating wealth or status or material possessions, become less compelling. The things that seemed abstract and distant, like the long-term survival of our species or the health of the biosphere, become more immediate and personal. This isn't just feel-good psychology. This is about survival. Humanity faces challenges that require long-term thinking and global cooperation. Climate change operates on multi-decadal timescales. Biodiversity loss requires thinking about ecosystem health over centuries. The threat of asteroid or comet impacts requires planning on timescales of millennia. Our brains didn't evolve to think on these timescales. We evolved in small tribes where the relevant timescale was seasons and years, where the relevant spatial scale was the distance you could walk in a day. We're psychologically adapted for immediate threats and immediate rewards, not for slowly unfolding catastrophes or long-term planning. But we can overcome these cognitive limitations through education, through cultivating perspective, through regularly reminding ourselves of our place in the larger context. This is what science communication is for. This is why I'm spending 4 hours talking to you about a comet, because understanding 3I Atlas is practice for the kind of thinking we need to navigate the challenges ahead. When you look at 3I Atlas and understand that it's traveled for millions of years to reach this moment, when you understand that it carries material billions of years old, when you understand that you're made of similar material delivered to Earth by similar objects in the deep past, it becomes a little easier to think on the timescales necessary for addressing climate change. It becomes a little easier to care about what happens 100 years from now, 1,000 years from now, 1,000,000 years from now. Because here's the thing, if humanity survives and continues to develop technologically, we will eventually become a spacefaring civilization. We'll establish permanent settlements on other worlds. We'll send probes and eventually crewed missions to other star systems. We'll encounter objects like 3I Atlas, not as distant telescopic targets, but as resources, as way stations, as objects we can land on and mine and study up close. Your descendants, if you have them, or the descendants of your generation, might someday stand on the surface of a comet like 3I Atlas, looking up at the stars, contemplating their place in the cosmos, just as you're doing now. The difference will be that they'll have perspective you can only imagine. They'll look back at Earth as a distant point of light, one world among billions. And they'll understand viscerally what you understand intellectually. That we're all part of one cosmic story, one grand narrative of matter organizing itself into ever more complex forms, eventually achieving consciousness, eventually reaching out to touch other worlds. But we only get there if we survive. If we don't destroy ourselves first through war or environmental collapse, or any of the other threats we've created. If we can find a way to extend our circle of concern beyond our immediate tribe to encompass all of humanity and all of the biosphere and the long-term future of our lineage, this is the ultimate personal meaning of 3I Atlas. It's a reminder of where we came from, what we're made of, and what we could become if we make the right choices. Let's talk about something that's been implied throughout this discussion but never made explicit. The sheer probability-defying nature of your existence. You are watching this video. You are capable of understanding the concept of a comet traveling from the Oort cloud. You can do calculus, or at least understand that calculus exists and that it allows us to calculate orbits. You can contemplate your own mortality, wonder about the future, feel awe at the vastness of space. Do you realize how unlikely that is? Start with the basics. For you to exist, Earth needed to form in the habitable zone of a stable star. That's not particularly rare. Current estimates suggest there might be tens of billions of Earth-like planets in our galaxy alone. But for you to exist, Earth needed to avoid catastrophic impacts during its formation. It needed to maintain liquid water on its surface for billions of years. It needed to develop a magnetic field that protects the atmosphere from being stripped away by solar wind. It needed to have a large moon that stabilizes its axial tilt, preventing wild climate swings. Then life needed to emerge. We don't know how likely that is. It might be inevitable given the right conditions, or it might be vanishingly rare. We have a sample size of 1. But somehow, somewhere on Earth, probably in deep-sea hydrothermal vents, or in tide pools, or in subsurface porous rock, molecules started replicating. Chemistry became biology. Then those simple replicators needed to survive for billions of years, evolving through countless extinction events. 5 major mass extinctions, dozens of smaller ones, ice ages, volcanic eruptions, impacts, climate shifts. Each one could have wiped out all complex life, reset the clock back to bacteria and archaea. But life persisted. it diversified. Single-celled organisms evolved into multicellular ones. Some of those evolved into animals. Some animals evolved backbones. Some vertebrates crawled onto land. Some of those evolved into mammals. Some mammals evolved into primates. Some primates evolved larger brains, developed language, created culture, and then, in just the last few thousand years, an eye blink in geological time, humans developed agriculture, writing, mathematics, science, technology. We went from stone tools to smartphones in what amounts to 0.0002% of Earth's history. For you specifically to exist, your parents needed to meet. Their parents needed to meet. Every single one of your ancestors, stretching back billions of years through fish and worms and single-celled organisms to the first self-replicating molecule, needed to successfully reproduce before dying. If any single one of them had failed, you wouldn't be here. Do you understand what I'm saying? You are the product of an unbroken chain of survival and reproduction stretching back to the origin of life on Earth. You are the temporary culmination of billions of years of evolution, of trial and error, of survival against impossible odds, and not just biological evolution. Cultural evolution too. You have access to knowledge that humans 500 years ago couldn't even imagine. You can learn in minutes what took scholars lifetimes to discover. You can watch videos explaining the orbital mechanics of comets while sitting on your couch eating food that was grown on a different continent and transported to you via a global supply chain that coordinates the activities of millions of people. The fact that you're able to contemplate 3-eye atlas, to understand what it is and where it came from and what it means, represents the success of the entire human project. All of our accumulated knowledge, all of our technology, all of our cultural transmission of information across generations, all of it working together to allow you, right now, in this moment, to connect with an object that's traveled for millions of years from the edge of our solar system. That's not mundane. That's not ordinary. That's miraculous. And here's what keeps me motivated. Keeps me excited about science and education and the future. You are not the end point. You are part of a continuing story. The knowledge you gain, the perspective you develop, the choices you make, they all influence what comes next. Maybe you'll become a scientist, contributing directly to our understanding of the cosmos. Maybe you'll become a teacher, passing on knowledge to the next generation. Maybe you'll become an engineer, building the technology that allows future missions to these distant objects. Maybe you'll become a political leader, making decisions that influence how we allocate resources to space exploration and planetary defense. Or maybe you'll do something that seems completely unrelated to astronomy, but you'll carry with you this cosmic perspective, this understanding of deep time and vast space. And it will influence how you treat other people, how you think about the future, what you value and prioritize in your life. Every single person who develops this perspective, who genuinely internalizes their connection to the cosmos, makes humanity slightly more likely to survive and thrive. Because the challenges we face require people who can think beyond the immediate, beyond the tribal, beyond the next quarterly earnings report or election cycle. We need people who can look at a comet like 3I Atlas and understand this is part of our family. This is part of our origin story. This is part of our future. And if we're smart and careful and lucky, our descendants will encounter objects like this, not as distant points of light, but as neighbors, as resources, as stepping stones to other stars. Let me tell you about one more thing, something that's been bothering astronomers about 3I Atlas and that might have significant implications for our understanding of the outer solar system. Remember how I mentioned that 3I Atlas is probably on a hyperbolic orbit, meaning it will escape the solar system? Well, here's what's strange. Its orbit is only slightly hyperbolic. The eccentricity is just barely above 1.0, which is the dividing line between elliptical orbits that stay bound to the Sun and hyperbolic orbits that escape. Dr. Matthew Holman from the Harvard-Smithsonian Center for Astrophysics pointed out that this is unusual. When objects get ejected from the Oort cloud, they typically fall inward with very high eccentricity, screaming past the Sun at high speed. But 3I Atlas is moving relatively slowly, relatively gently. This suggests something subtle nudged it inward, not a close stellar encounter which would give it high velocity. Not a major gravitational perturbation from a massive object which would create a more obviously disturbed orbit. Something gentle, something distributed, something like, what if there's something out there we haven't detected yet? Something massive enough to gravitationally influence Oort cloud objects, but distant enough and dark enough that we haven't spotted it. I need to be careful here because this is where legitimate science shades into speculation and where speculation can shade into pseudoscience. There have been proposals for a Planet 9, a hypothetical world several times more massive than Earth, orbiting far beyond Neptune, too distant and too dark to have been detected by current surveys. Some researchers, like Dr. Konstantin Bettigen and Dr. Mike Brown from Caltech, argue that there's good evidence for such a planet based on the clustering of orbits of certain distant Kuiper belt objects. Other researchers are skeptical, arguing that the apparent clustering could be a selection effect, an artifact of when and where we've pointed our telescopes. The debate is ongoing and heated, as scientific debates often are when data is limited and interpretation is uncertain. But here's what's not debatable. There are large regions of the outer solar system that we've never surveyed. There could be objects out there, massive objects, that we simply haven't found yet. Not planets necessarily, but maybe a population of supercomets, objects intermediate in size between comets and dwarf planets like Pluto. The orbital characteristics of 3I Atlas could be a clue. If we find more objects with similar orbital properties, gently nudged inward from the Oort cloud, It might point to a specific region of space where something massive is lurking, gravitationally shepherding objects into certain orbits. This is exciting because it means we might be on the verge of discovering something significant about the architecture of our solar system. Not just cataloging more objects, but understanding the hidden structures that govern their movements. The invisible gravitational landscape that shapes the orbits of trillions of distant worlds. And this brings us back to something fundamental. How much do we really know about our own solar system? We like to think we've got it figured out. We've mapped the planets, we've sent probes to most of them, we've catalogued hundreds of thousands of asteroids and comets, but the solar system is vast. The region of space gravitationally dominated by the Sun extends out to roughly 100,000 astronomical units, nearly 2 light-years. The volume of that space is incomprehensibly large, and we've directly observed only a tiny fraction of it. Every new survey discovers thousands of previously unknown objects. Every improvement in telescope technology reveals details we couldn't see before. Every unusual object, like 3I Atlas, raises new questions and hints at new discoveries. We are still in the early stages of understanding our cosmic neighborhood. We are still explorers, still making first contact with worlds and phenomena that have existed for billions of years, but are only now revealing themselves to human observation. And you are living through this era of discovery. You have front row seats to one of the most exciting periods in the history of astronomy. Within your lifetime, we might discover that hypothetical Planet 9, if it exists. We might catalogue the entire population of large objects in the Kuiper Belt. We might send probes to dozens of comets and asteroids, returning samples, revealing their compositions, their structures, their histories. Each discovery will refine our understanding. Each new piece of data will update our models, and each update will change how we see our place in the cosmos, how we understand our origins, how we plan for our future. 3I Atlas is one piece of this larger puzzle. It's one data point in a dataset that's growing every night as telescopes around the world and in space scan the sky, looking for moving objects, measuring their properties, calculating their orbits. And the beautiful thing is, you can participate in this. Citizen science projects allow anyone with an internet connection to help classify astronomical images, search for asteroids, discover comets. Professional astronomers need help processing the massive amounts of data generated by modern surveys. They need people to look at images, identify interesting objects, flag anomalies. You could discover the next 3I Atlas. You could be the person who first notices an unusual object in survey data, triggering follow-up observations, contributing to human knowledge. It's not just theoretical. Amateur astronomers and citizen scientists make significant contributions to astronomy all the time. So that's another way that this story is personal. You're not just a passive audience member learning about discoveries made by other people. You can be part of the discovery process itself. You can contribute. You can matter.
We're approaching the end of our journey together. But before I bring this to a conclusion, I want to address something important: the role of uncertainty in science. Throughout this video, I've presented a lot of information as if it's established fact, but the truth is more nuanced. Much of what I've told you represents our current best understanding, based on the available evidence, but there are uncertainties and open questions everywhere. The size of 3I Atlas? We've narrowed it down, but we don't have a precise measurement. It could be 5 kilometers, could be 10 kilometers, could be something in between, or even larger. The composition? We know some of what's in the coma, but we don't know the full inventory of molecules, and we especially don't know what's in the interior of the nucleus, hidden beneath the surface layers. Its orbit? We've calculated it with high precision, but small uncertainties in position measurements translate to larger uncertainties in long-term trajectory. We're confident it's on a hyperbolic orbit, but we can't be absolutely certain it won't return in a few million years. Whether it's fragmenting? The observations are consistent with fragmentation, but they're also consistent with other explanations, like an elongated, tumbling nucleus or localized jets of activity. This uncertainty is not a weakness of science. It's a feature, not a bug. Science advances by acknowledging what we don't know, by quantifying our uncertainties, by constantly testing and refining our models against new observations. The scientific papers about 3I Atlas don't claim to have all the answers. They present evidence, propose interpretations, discuss alternative explanations, quantify uncertainties. This is how the process works. This is how we gradually converge truth. And it's important for you to understand this because we live in an era of information overload where confident-sounding claims are everywhere, where conspiracy theories and pseudoscience present themselves with absolute certainty, where admitting uncertainty is seen as weakness rather than honesty. Science is the antidote to this. Science is the practice of saying, here's what we think we know, here's how confident we are, here's what would change our minds, here's what we're still uncertain about. It's the practice of proportioning your confidence to the strength of the evidence. When astronomers say 3I Atlas is probably between 5 and 10 kilometers in diameter, that probably is doing important work. It's acknowledging uncertainty while still giving you useful information. It's being honest about the limitations of our knowledge while sharing what we've learned. This is the mindset I want you to cultivate. Not blind acceptance of authority, not knee-jerk skepticism of everything, but thoughtful evaluation of evidence, comfort with uncertainty, willingness to update your beliefs when new information arrives. This mindset is valuable, not just for understanding astronomy, but for navigating life. How do you make decisions when you don't have complete information? How do you balance confidence and humility? How do you distinguish legitimate expertise from confident ignorance? The story of 3I Atlas teaches you this too. It's not just about a comet. It's about how we know what we know, about the process of scientific inquiry, about the value of evidence-based reasoning. And it's about something else too, the power of curiosity. Every discovery in this story, from the initial detection of 3I Atlas to the recognition of its outburst, to the ongoing analysis of its composition, happened because people were curious. They wanted to know what that moving dot of light was. They wanted to understand why it suddenly brightened. They wanted to figure out what it's made of and where it came from. Curiosity drives everything. It drove early humans to look up at the night sky and wonder what those lights were. It drove ancient astronomers to carefully track the movements of planets and comets. It drove Galileo to point his telescope at Jupiter and discover moons orbiting another world. It drove the space age, the development of planetary probes, the construction of massive telescopes. And curiosity can drive you. Whatever you're curious about, whatever questions keep you up at night, whatever puzzles seem interesting to you, pursue them. Learn about them. Maybe you'll make a contribution, maybe you won't, but the pursuit itself is worthwhile. The cultivation of curiosity, the development of understanding, the connection with something larger than yourself. That has value independent of any practical outcome. 3-Eye Atlas sparked curiosity in astronomers around the world. It sparked curiosity in you, or you wouldn't have watched this far. Hold on to that feeling. Let it motivate you. Let it connect you to the long chain of curious humans stretching back to our earliest ancestors, all asking the same fundamental questions. What's out there? Where did we come from? Where are we going? So let's bring this home. Let's talk about what 3-Eye Atlas means in the biggest picture possible. 3-Eye Atlas is a messenger from the deep past and the deep cold. It formed billions of years ago, in the early days of our solar system, from the same cloud of gas and dust that eventually became the sun and planets. It was ejected to the outer reaches by gravitational interactions with the giant planets. It spent billions of years in the Oort cloud, frozen, dormant, slowly accumulating cosmic ray damage, occasionally jostled by passing stars or density waves in the galaxy. And then recently on cosmic timescales, but millions of years ago on human timescales, something nudged it. A gentle gravitational push, maybe from a passing star, maybe from that hypothetical planet 9, maybe from the collective gravitational influence of the Milky Way itself. Its orbit changed. It started falling inward, accelerating under the sun's gravity, beginning a journey that would take millions of years and cover trillions of kilometers. As it approached the inner solar system, the sun's warmth began to affect it. Its surface started to sublimate. It developed a coma, then a tail. It became visible to our telescopes, a moving point of light against the background stars. We discovered it. We named it. We studied it. And it revealed that it's larger and more complex than we initially thought, forcing us to reconsider our models of the Oort cloud, of cometary composition, of the hidden architecture of our solar system. Soon, on cosmic timescales, it will reach its perihelion, its closest approach to the sun. It will experience maximum heating, maximum stress. It might survive intact. It might fragment into dozens or hundreds of pieces. Either way, it will then begin its outward journey, accelerating away from the sun, probably never to return, escaping into interstellar space, beginning a new journey that might last billions of years more. That might eventually bring it close to another star, into another solar system, where perhaps other beings will discover it and study it and wonder about its origins. That's the physical story. But there's a deeper story, the story of meaning, of connection, of perspective. 3-Eye Atlas connects you to deep time. When you look at it, you're seeing matter that's older than complex life on Earth, older than the continents, older than the oceans, older than the atmosphere you breathe. You're seeing the raw materials of the solar system, preserved in pristine form. It connects you to deep space. The distances involved, the scales, the vast empty regions between objects, all of it challenges your intuition, forces you to think beyond the human scale, beyond the familiar. It connects you to the ongoing story of discovery. Right now, as you're watching this, there are astronomers observing 3-Eye Atlas, analyzing data, refining models, preparing papers. The story isn't finished. New observations might change our understanding. The comet might do something unexpected. Science is happening in real time, and you're part of the audience, witnessing the process. And most importantly, it connects you to your own origins. You are made of star stuff and comet stuff. The water in your body was delivered by objects like 3-Eye Atlas. The organic molecules that make up your cells might have originally formed in environments similar to cometary interiors. You are not separate from this cosmic drama. You are part of it, temporarily assembled into a form capable of understanding and appreciating the whole magnificent story. So what do you do with this knowledge? How does understanding 3-Eye Atlas change how you live your life? Maybe it gives you perspective when things seem overwhelming. When you're stressed about work or relationships or money, You can remember that you're a temporary arrangement of atoms on a small planet orbiting a medium-sized star in an average galaxy. And in the grand scheme of things, your problems are infinitesimally small. That's not meant to diminish your problems. They're real and they matter to you, but it can provide context, can make them feel more manageable. Maybe it inspires you to learn more, to cultivate curiosity, to never stop asking questions. The universe is vast and strange and full of wonders, and every answer raises new questions. And that's not frustrating. That's exhilarating. You'll never run out of interesting things to learn about. Maybe it motivates you to contribute, in whatever way you can, to the collective human project of understanding and surviving and thriving. Maybe you'll support space exploration, or science education, or environmental conservation, or any of the countless efforts aimed at ensuring that humanity has a long-term future, that our story doesn't end prematurely. Or maybe it just gives you a sense of wonder, a feeling of awe, a momentary transcendence of the everyday concerns that usually occupy your attention. Maybe sometimes, when you're having a hard day, you'll look up at the night sky and remember that there's a comet out there, moving through the darkness, carrying messages from the deep past, and you'll feel connected to something larger than yourself, and that will be enough. That's the gift of cosmic perspective. That's what astronomy offers, beyond the practical applications, beyond the planetary defense and the resource utilization and the technological spin-offs. It offers meaning. It offers connection. It offers a sense of place in the grand narrative of the cosmos. And 3I Atlas, this object that was completely unknown to humanity just months ago, this ancient traveler from the edge of our solar system, has become part of your story. You know about it now. You understand what it is and what it means. You've spent 4 hours learning about it, contemplating it, connecting with it. That matters. That has value. Not because it will make you money or advance your career, though understanding science might do those things too, but because it expands your consciousness, enriches your experience, connects you to something eternal and profound. Let me end with a thought experiment, something to carry with you as you continue your journey through this strange and beautiful universe. Imagine it's 1 billion years from now. Humanity, if we've survived, has become something we can barely imagine. We've spread throughout the galaxy, maybe beyond. We've evolved, both biologically and technologically, into forms that would seem like gods to our present-day selves. And somewhere, in some database containing all of human history, all of our accumulated knowledge, there's a record of 3I Atlas. There are the observations from October 2024, the measurements, the spectra, the calculated orbit. There's this video, or some future analog of it, explaining what it meant to people of the early 21st century. And some far future version of a human, something that evolved from us, but might not be recognizable as human anymore, might access that record and think about their ancestors, about us, about how we were just beginning to understand our place in the cosmos, how we were taking our first tentative steps toward becoming a spacefaring civilization. They might feel a connection across deep time, similar to the connection you feel when you learn about ancient humans painting on cave walls, or building stone monuments, or looking up at the stars and wondering. We are the ancients of the far future. Our struggles, our discoveries, our moments of wonder and awe, they're all part of the long story that leads to whatever comes next. 3I Atlas will be remembered, if anyone is around to remember it, as one of countless objects that taught us about our cosmic environment, that helped us understand where we came from and where we might be going, that inspired us to keep exploring, keep questioning, keep reaching out into the darkness. And you, by learning about it, by caring about it, by spending time understanding what it means, you're honoring that tradition. You're part of the unbroken chain of curious humans, stretching from our earliest ancestors to the far future, all driven by the same fundamental desire to understand. So thank you for joining me on this journey. Thank you for caring about a comet most people will never hear about. Thank you for cultivating curiosity and cosmic perspective. Thank you for being part of the ongoing story of humanity's relationship with the universe. 3I Atlas came from the darkness and will return to the darkness. But for a brief moment, it passed through our cosmic neighborhood and revealed secrets about the solar system, about the nature of comets, about the hidden architecture of the space around us, and about our own origins and connections to the wider cosmos. It got bigger in our understanding, not just physically, but conceptually. It grew from a simple comet to a symbol of everything we've discussed: the vastness of space, the depth of time, the chemical connections between whole matter, the fragility and resilience of existence, the power of curiosity, the value of scientific inquiry, and the profound meaning that comes from understanding our place in the cosmic order. Keep looking up. Keep asking questions. Keep learning. Keep connecting with the cosmos. Because you are made of stars and comets and supernova. You are the universe contemplating itself. You are a temporary arrangement of atoms that has the extraordinary privilege of being conscious, of being able to wonder and learn and understand. And out there, somewhere beyond the planets, moving through the cold darkness, 3I Atlas continues its journey, carrying its cargo of ancient ice and organic molecules, oblivious to the fact that it briefly captured the attention and imagination of conscious beings on a small blue world. Beings who looked at it and saw not just a comet, but a messenger, a teacher, and a mirror reflecting back our own cosmic story. That's what 3I Atlas means. That's why it matters. That's why we care. And that's why you should never stop looking at the sky and wondering what else is out there, waiting to be discovered, waiting to teach us something new about ourselves and our place in this vast, ancient, beautiful cosmos we call home. Thank you for watching. Clear skies, my friends. And remember, you are part of something much larger than yourself, much older than you can imagine, and much more wonderful than words can fully express. Now go out there and live your life with cosmic perspective. Look at 3I Atlas one more time, if you can find it in the sky or in an image online, and remember everything we've talked about. Let it change you. Let it inspire you. Let it connect you to the eternal dance of matter and energy that has been unfolding for 13.8 billion years and will continue for trillions more.